All right, let's get right into it. We're talking about an experiment so important, so revolutionary, that it didn't just win Einstein a Nobel Prize. Oh no, it created an entirely new branch of physics and totally flipped our understanding of the universe on its head. Yeah, it's a pretty big deal. You see, for pretty much the entire 19th century, this was a done deal. It was settled science. Thomas Young's famous experiments showed light behaving exactly like a wave, creating interference patterns, bending around corners. All the evidence, everything pointed to light being a wave. He had even managed to prove the one and only Isaac Newton wrong. Or so everyone believed. But then, an experiment came along that just didn't add up at all. An experiment whose results challenged absolutely everything physicists thought they knew for sure. This, my friends, is the story of the photoelectric effect. Now, the setup itself sounds simple enough, right? You've got a negatively charged metal plate, we'll call that the emitter. Facing it is a positively charged plate, the collector. And this whole scene is happening inside a vacuum, so no air can get in the way. The big idea was to just shine a light on that first plate and see if you could knock any electrons loose, so they'd jump across to the other side, which would create a measurable electric current. Simple? Okay, this is where things get really, really weird. Look at the massive difference between what should have happened according to wave theory and what actually did. The old theory said brighter light, more intensity, should mean more energy, right? So it should have kicked out electrons with more speed. It also predicted that if the light was dim, there'd be a bit of a time lag while the energy built up. But nope, none of that was true. The electron's energy depended on the light's color, its frequency. The electrons shot out the instant the light hit. And, maybe weirdest of all, if you used a frequency that was too low, absolutely nothing happened. You could blast it with the brightest light in the universe, and not a single electron would budge. The old theory didn't just have a few cracks, it was completely, utterly wrong. So this was the giant puzzle that had everyone scratching their heads. How could any of this be possible? It was like the electrons were being punched off the surface, not gently nudged by a building wave of energy. And why on earth did the color of the light matter so much more than how bright it was? To really wrap your head around just how strange this was, let's try a little analogy. Imagine our electron is a big melon sitting on a table. Your challenge is to knock that melon off the table. So, for our first attempt, we're going to throw a stream of cherry tomatoes at it. These little guys represent low-frequency light. Think red light. And, well, as you'd expect, there's just not enough kick in a single tomato to do anything. You could stand there all day throwing them one by one. That melon is not going anywhere. Okay, you might think, what if we just turn up the intensity? Let's throw a whole bucket, a flood of cherry tomatoes at it all at once. But it makes no difference. It doesn't matter how many you throw simultaneously, not a single one has enough oomph on its own to move that melon. Still a total failure. All right, new plan. Let's try something with a bit more heft. How about one single lemon? This lemon represents a higher frequency light, like blue or ultraviolet light. And, wow, just one is all it takes to send that melon flying right off the table. That's the key. This is what we call the threshold frequency, the absolute minimum energy you need in a single projectile to get the job done. This absolutely baffling result called for a completely new, totally radical idea. And in 1905, a young Albert Einstein stepped up and suggested that, hey, maybe we've been thinking about light all wrong. Einstein's big idea was that light isn't some continuous flowing wave after all. No, instead, he said it's made of tiny individual packets of energy. He called these packets quanta, and today we know them as photons. And this image here shows the concept perfectly. Instead of a gentle wave washing over the metal, it's more like a hailstorm of these tiny energy bullets hitting the surface. Each individual photon collides with one and only one electron in a single all-or-nothing event. Now, being Einstein, he didn't just stop with a cool idea. He backed it up. He described this whole interaction with a stunningly simple yet incredibly powerful equation that neatly explained every one of those strange observations. And there it is. Looks pretty simple, right? That little formula won him the Nobel Prize, and it literally changed the world. So let's break it down. On the left side, you have HF. That represents the total energy carried by one single incoming photon. The F is for frequency. That's what determines the light's color. And that h is something called Planck's constant, a fundamental number woven into the fabric of our universe. It's the magic link that connects a photon's frequency directly to its energy. And just like that, this one term explains why color, not brightness, was the key.
Okay, so that photon's energy gets used for two things. The first thing it has to do is pay what's called the work function, which you see here as a capital W with a little zero. You can think of this as the exit fee for the electron. It's the bare minimum energy cost to just pry an electron loose from that particular metal. And every type of metal has its own unique exit fee.
So let's put it all together now. A photon comes in carrying its total energy, hf. It immediately pays the exit fee, that work function W0, to free the electron. And any energy that's left over, well, that becomes the electron's kinetic energy, Ke max. That leftover energy is what determines how fast the electron zips away. This one equation perfectly explained everything. If the photon's energy, hf, wasn't big enough to pay the fee, well, then nothing happened, just like our cherry tomatoes. It all made perfect sense. And this discovery, it did so much more than just solve one tricky experiment. It basically kicked open the door to a whole new and profoundly bizarre way of looking at reality itself.
Which brings us all the way back to the beginning. If Einstein was right, and light is a particle, did that mean a whole century of physics was just wrong? Was Thomas Young's elegant wave theory a huge mistake? And this is where your brain might start to melt a little bit. It turns out they were both right. Light is a particle, and it's a wave. At the same time. It just decides to act like one or the other, depending on what kind of experiment you're doing. This mind-bending concept has a name: wave-particle duality.
Now, if that sounds deeply, deeply weird and confusing, good. You're in excellent company. The legendary physicist Richard Feynman, a guy who won his own Nobel Prize for this stuff, once famously said this. So yeah, even the absolute masters of the field think it's bizarre. Its strangeness is actually what makes it so amazing. So you see, the photoelectric effect wasn't just another experiment. It was a wake-up call. It taught us that down at the tiniest, most fundamental levels, the universe just doesn't play by the rules we're used to. And that leaves us with one final, thrilling thought. If something as basic as light can have a secret dual identity, what other incredible, mind-bending mysteries is our universe just waiting